out or not, we'll see. I'm going to use Desmos because it just makes a nice bigger screen for me, but we're going to work with, starting with some of the calculus that goes with parametric equations. So today, mainly finding first derivatives, second derivatives, and where there's vertical and horizontal tangent lines to the graph. So you're going to have to page forward a little bit. And just to remind you, I just got shot, how to eliminate the parameter when it's tricky. I won't have you do that more than once on the test because it's actually the pre-calc of it. But remember I said when it's tricky, you should maximize the fact that cosine squared plus sine squared is equal to 1. And write these each in terms of cosine and sine. So for this guy, I already have it screenshot in here, but I just go x minus 4 over 2 is cosine, and then I square it. And then for the next one, I get y plus 1 divided by 2 would be sine, and I square it and set it equal to 1. And if I had asked you to predict what that was going to make, parametrically, we said on Friday that if the coefficients are tied, and it's sine and cosine, it makes a circle, right? With a radius of whatever the number up front is. So this is a circle with a radius of 2, and the plus 4 and the minus 1 just shift it 4 to the right and 1 down. So if we graph that, you should know what it's going to make. A lot of times we'll multiply through by that denominator to get it back to the algebra 2 form of the circle. And then just to remind you, what do you lose when you eliminate the parameter graphically? Like this versus this, what do you lose on the graph? What'd you say? Well, sort of. Yes, like graphically, this one you could only graph like the top half or the bottom half. But when we did the parametric, what was the couple things we had control of? Do you remember, like on our calculators? Speed, yeah, and the direction of it. So that's what you lose when you eliminate the parameter. Now we're going to start going into the calculus of it. So we're going to be finding the first derivative. It still means what it's always meant, which is the slope of the tangent line to the curve. So it's going to be the exact same thing. The only difference is the curve is defined in terms of t. So to find dy dx, like maybe the function, one of them we do today is going to make a bow tie. And if I want to find the slope of this tangent line right there, I would need the first derivative or the dy dx, but the curve is defined in terms of t. So you just do dy dt over dx dt. You do need to memorize that, but it kind of makes sense because if you multiply by a reciprocal and sort of picture these canceling, you can kind of see that that will give you the first derivative. So first derivative gives you the same information it always has. You just find it a little differently, but it's pretty easy. So when it says to find dy dx, or the slope of the tangent line, or an equation for the tangent line, you would first of all do dy dt, and I'm not going to write it out after this, I'm just going to do it once, but you basically just do 2 derivatives and then divide them. So if I did the derivative of x with respect to t, I would just get 2t, and if I did the derivative of y with respect to t, I would get, oops, I did it backwards. I was just going to say the biggest mistake is doing it upside down. It's dy dt. So on the top would be a 3t squared, and on the bottom would be a 2t. That's it. Like you just take the top and the bottom separately. So this guy would become 3t over 2. And now your derivative is a function of the t, or generally that's the time. So when it says to find it when t is 3, you just t equals 3, and then t equals 3, and then t equals 3. And it'd be 9/2, and it tells you that the function at that time is curving up pretty rapidly. Does that make sense? So it's very straightforward. You can be asked now all the Calc AB questions about tangent lines. Like if I said to find the equation for the tangent line when t equals 3, what 2 things do you need for the equation of a tangent line? Slope, which I just found, and a point, but the point's now a function of t. So when t is 3, my point would be 9, 27, and I'd still have, so it's just kind of an added layer, but really not much we need to discuss a whole lot with that. This guy right here, we're going to do first, and then we'll graph it. So here's my parametric curve, X is being pulled by sine of t, y is being pulled by sine of 2t. I'm being asked for the first derivative at different spots along the curve. So we're going to go fairly fast because really derivative in parametric is just two derivatives with respect to t. So my dy dx would equal dy dt. So what's the derivative of that guy, Priestley?
2 cosine 2t.
Yeah, so we're just going to do a 2 cosine 2t on the top, nice and easy. And on the bottom, the derivative of sine is cosine. So that's the one we're going to be using for all of these, and then we're going to confirm it on a graph. So my dy dx, when x is equal to pi over 6, requires a little bit of our unit circle. So we just have to make sure we remember when we put in a pi 6, we'll have 2 cosine pi thirds on the top, because we're multiplying by 2, and on the bottom, cosine pi over 6. Just convince yourself that you remember your unit circle fairly well. So I'm just going to, if you need to draw it, that's fine. I'm just going to wait, because if I always do the unit circle for you, you think you have it down, and maybe you don't. So you shouldn't be debating between more than two things for that, right? What are the two things you're kind of trying to decide between for cosine pi thirds? What are the two numbers? 1/2 or root 3 over 2. Be 100% sure you know which one it is. Which one is it? 1/2 or root 3 over 2? It is 1/2. However you have them memorizing that, we've done it so many times, but it's this one over here. You can even kind of see that the cosine or the x is halfway, or you use your triangle, whatever you need to do. But that's going to be 2 times 1/2, which is 1. And then on the bottom, what's cosine pi over 6? This guy over here. Root 3 over 2, yeah. So, and then we don't leave compound fractions, so it's 2 over the square root of 3. Or 2 root 3 over 3 if you had to. It's positive, so it means at that time, the curve is going uphill. We'll go graph it in a little bit. So you guys go do pi fourths. So go do dy dx when x equals pi over 4. Tell me what you get. And then we have to interpret it in the context of the curve. If you can take derivatives and you understand particle motion, and you can do simple integrals, like this chapter is just kind of stuff you've done before, just with another layer to it. What do we get for that one? What's cosine pi halves?
0.
0. Yeah, so, and I doubled the pi fourths to get the pi halves. So this is 0 over, I don't care because it's non-zero. It's root 2 over 2. So we have to remember from Calc 1, what does it mean when you have a derivative that's 0? What's going to happen on my curve at that place? What do you think? Not necessarily. Even more simple than that. I mean, it could be a max or a min, but for sure, since you know that the derivative is 0, there's a what there? There it is, horizontal tangent line. It might peak out there, but it might not. Okay, so yes, that would be 0. So I'm going to put here horizontal tangent line. So kind of think about ahead. It used to be that when you were finding where there are horizontal tangent lines, you would just set the derivative equal to 0. But now your derivative is kind of dependent upon two things, the top and the bottom. So notice it's when the top is 0 or just dy dt. So you might want to write that dy dt equaling 0 implies horizontal tangent lines, which makes sense because x isn't moving and only y is. So it should make a lot of sense. Go to the next one at what? Pi halves? Dy dx at pi over 2. While you guys are doing that, I'm going to bring up the curve and kind of show you. You can do it on your graphing calculator. I taught you how to do that already. It's faster for me to do it in Desmos. This guy is sometimes called the bow tie curve because it looks, whoops, that's not the one I wanted. It looks like a bow tie. So if you want to, actually try doing it on your calculator just because there's been a weekend. See if you remember. In Desmos, all I have to do is enter it as an ordered pair, sine t, sine 2t, which is why it's a little easier. I also don't really need to mess with anything because I can zoom in and zoom out with my fingertips. But if you guys go, remember you go to mode, you go to parametric, and you weren't here previously. Do you have your calculator? Oh, you're using it on there. So go to parametric mode. And remember that, what did we say, just because there were a couple people gone on Friday, what did I say to put in for the t step? 0.1 or 0.01, because otherwise it tends to get very rigid. So, and if you wanted to go faster or slower, you're in control of that. So in parametric mode on your calculator, like a lot of you probably never even knew that was in there, you can graph, we'll be graphing flowers and hearts and all kinds of goofy things in polar. In parametric mode, but we made the Jimmy Neutron symbol on Friday. But this guy right here, we said that when t equaled pi over 4, we had a, which one was it when t equaled, which one did we have the horizontal tangent line for? Pi fourths. So you can kind of see like where it's split there, we have a horizontal tangent line, vertical, horizontal. So you're finding all those slopes of the tangent lines. This blue curve I have is for the next one I graphed. It's for our next example. But did anyone not get it to graph? You good? And because it was sine, do you remember what I said just for TJ's? When you're setting your x min and max, I go 0 to 2 pi. And what did we say for the sines and cosine ones for the y's? Just so it looks nice. What's the most sine can ever be? There you go. What's the most sine can ever be? 1. What's the least? -1. So I like to go from -1 to 1 so it takes up my whole screen. And then, TJ, we also talked about if you hit zoom square, it'll square the window up and make it look nicer. Were you able to get it to graph?
Yeah.
Okay, awesome. Just making sure we're catching everybody up here. So, I won't have you graph really anymore on your calculator. For the AP test, they graph them for you, so that the pre-calc doesn't mess you up. All right, so off on to the next page. The second derivative is weird. Okay, so watch here. The second derivative is still the derivative of the first derivative. So it's still like the derivative with respect to x of the first derivative. If you go replace the y right here with the y prime, we'd get this. The second derivative, it's got just like a weird glitch to it. It equals the derivative of the first derivative with respect to t over dx dt. That looks really weird. I'll show you it looking a little better in just a second. So really, it's the derivative with respect to t of your dy dx all over dx dt. And I'm going to give you kind of the short thing in your head to think about, because you don't want to have to memorize that, do you? There's a lots of d's and y's and x's and t's, and it's really quite easy to memorize. But just to prove it to you, you don't write this down, okay? Division's the same as multiplying by the what? So if I just don't, you write it down, it'll mess up your notes. But if I just multiply it by this, the dt's will cancel. Do you see it? Do you see how I have d squared y over dx squared? Can you see it? So the weird thing about it is this guy right here. So point at it, because your gut is going to tell you. So back to that last example. If you're doing the second derivative, the first thing you do is just take the first derivative. So let's just write, take the first derivative. You're just going to do dy dt over dx dt, just like you've always started a second derivative. So again, I have a real simple one because it's just for procedure. But if you're taking a second derivative, you just hop on and you take the first derivative. And the first derivative of this would be dy dt over dx dt. And then you're going to clean it up and get 3t over 2. Kids who don't pay attention would say, well, the derivative of that is 3/2. And they just take the second derivative. So make sure you take the remaining derivative, I'm just going to put d, and let's put like derivative with respect to t, just so I don't want to write the remaining derivative with respect to t. My second derivative is going to equal, what is the derivative of this guy with respect to t? What is the derivative of that? 3 halves. That's not the answer. That is, I'm going to go back up here. That's this part. You took the derivative with respect to t of the first derivative. But then what does it say to divide by? Dx dt. All right? So you just have to take and say all over dx dt, which is 2t. So this guy would be 3 over 4t. So that little dividing by dx dt is kind of weird, but it's there. So you basically, again, you just take the first derivative as you normally would, then take its derivative as you normally would, but then what do you have to remember, divide by? Dx dt. So go with your gut until the very end, and then don't quit. Divide by dx dt. All right, and that'll make it easier. So you're going to do the first derivative. So let's move on and go to our next guy here. Take a look at this. This is a parametrically defined function that you guys have had since you were in Algebra 2. That the unit circle is the first parametrically defined function you ever had. You just didn't know that it was parametrically defined. And for the unit circle, what is t usually? Instead of a t, what do they call it? Theta, right? So it's usually just an angle. So this says to find dy dx and d squared y dx squared, or the second derivative, at pi fourths. So we're still getting the same information. The first derivative will tell us if the function's increasing or decreasing there and by how much. And what does our second derivative always tell us about a function? Concavity there. So I actually know, just because I understand Calc 1, that I'm going to get a negative and another negative for my first and my second derivative. So let's go up here and find our first derivative. So our first derivative is going to be dy dt over dx dt. So basically it's just twice the amount of work to take a derivative in parametric, because you have to do 2 derivatives. So I'm going to go back up here and do dy dt. Derivative of sine is cosine. So I'm going to have cosine t. And what's the derivative of cosine? Negative sine. I was supposed to do this at pi fourths, so I'm just going to tack it on right now so I don't have a linkage error. Pi fourths, right? What is the slope of that tangent line at pi over 4? Because that's what you're finding. What is the slope of that tangent line? These guys are the same at pi fourths, correct? So what's this going to be? Negative 1. That's still giving you the slope of this tangent line. It's eventually going to be called tangential velocity. Like if something was moving along here, just that's its speed. Sort of. All right? So it's eventually going to be tied into motion. The next thing up is the second derivative. So when we do our second derivative, you don't really need to restart if you were listening, right? You do the first derivative, which we already did, right? Over there. We're going to do cosine t over, negative sine t. But then what do we have to do with it? Take its derivative with respect to t, and then divide it by dx dt, which is what? Negative sine t. So here's my question for you. How do you want to find the derivative of this stuff right here? You have 2 options. I don't care. But how do you want to take the derivative of cosine t over negative sine t? Give me a way. That one? What? You could do quotient rule. Always say, because you never forget that, correct? Or what is cosine over sine? Cotangent. Do you remember its derivative? Negative cosecant squared. Which if you do, that's fine. If you don't, that's what you'll get if you do the what? Quotient rule. So since I know we all know the quotient rule, and since Lindsay did remember that that is negative cosecant squared, right? If you didn't remember, oh, actually be positive. because this is negative cotangent. So it'd be like that. Now, what is cosecant squared? Because I don't like dealing with cosecant. What is it? 1 over
1 over
sine squared. So this is actually sine cubed. A lot of trig in here, but I'm just going to repeat what we did. Here's our first derivative. Here's the derivative of it. But in parametric, we always have to divide by dx dt. So you go with your gut and then divide by dx dt. I asked how to find the derivative of this. You could have done quotient rule, or you remember the derivative of cotangent. That's up to you. This is my answer, but I need to do it where? Pi over 4. So I actually have to do negative 1 over. And what's sine of pi over 4? What is it? Come on, help me out. Root 2 over 2. And I need to cube it. And if that's multiple choice, you need to know how to get that answer. So I'm going to let you guys have at it. Obviously, you're going to flip it first and make it a negative 2 cubed over root 2 cubed. But that's kind of where we choke, if anything, is right at like those very end things. So I kind of want to make you do it. And I did go fast because this is kind of easy. So you slow me down if you guys are pretty good about that too. What's the square root of 2 cubed? 4. Root 2 times root 2 times root 2. Also known as 2 root 2 or root 8, but I like to use over 2 times root 2 root 2 would be 2 root 2, right? 2 root 2. So I'm going to have a negative 4 over root 2. What if you don't see that? Yeah, you could take, I'm not going to teach you how to rationalize the denominator at this level, but if you don't see it, try it. All right, so are we good with the second derivative? We do the first derivative, then we do it again, and then we remember to divide by what? Dx dt. Then you don't have to memorize the formula because it is almost exactly what your gut would say. All right, so here it goes. We've got 2 more examples. For the curve given by x is the square root of t, and y is this one, it says find the slope and concavity at this point. So the first thing you have to know is what's t. So I'm going to let you guys figure it. It didn't say when t equals 7 or t equals 3 or t equals 1. You guys have to know when you're going to stop. T is controlling both of them. You're going to stop it when t is something and find the first derivative, the slope, and the second derivative, the concavity. So let me think that out. Which equation is easier to work with, the x or the y? X. So I would just say 2 has to equal root t. What's t? 4. So sometimes you're going to have to use intuition for the t. So t is equal to, I actually just bumped up the difficulty a lot on this one because I just wanted to get the skills down, and now we'll. So it says find the slope. So first thing up is dy dx. You guys go do it without looking up here. I just don't, you have to wait for me to write it, so I'm going to get it started. Oh, that's just t minus 1, isn't it? kind of putsy. And then go do it when t equals at that point, which would be when t equals 4. You guys good? So here's my first derivative, the derivative of y with respect to t, and the derivative of x with respect to t. I don't like compound fractions. When I go put in a 4, I'm looking like 4 to, I'm going to have a 12. That means it's going up very, very steeply at that instant in time. Okay? It is rising way more than it's running. Does that make sense? All right, for my second derivative, it gets a little more complicated, but you do what you would think you would do. You take the derivative of your first derivative. I wouldn't do quotient rule on this one. I would do the derivative on that, but I even wouldn't use product rule. What do you think I would choose to do with that? You could do first d second plus second d first, but that's going to get messy. What I would just, use all those A-B little tricks. This is really going to be 2t to the 3/2 minus 2t to the 1/2 if you write it out. And I would just use the power rule. So my second derivative will be the derivative of this guy. So what's that going to be? 3/2 times 2. I'm getting a t cubed. Is that right? Yes. So it'll be t cubed minus t. Is that right? I'm just making sure. T to the 1/2. Brought it out front. I think I'm good, aren't I? Then what do I need? This was my first derivative, correct? Is this my second derivative? Yes or no? You guys are feeling me really quiet. Is this my second derivative? What's wrong with it? I didn't divide by dx dt. And what was dx dt? Something doesn't feel right, though.
Derivative, right?
Yeah.
There's a 3 in front of that t.
Oh, it's a 3. You are so right. It's a 3t to the 1/2 minus. I forgot to knock the power down around. Something felt really off. And I saw a couple eyeballs like this. It's like, okay, sorry, I brought it out front and didn't knock it down one. That's deadly. I've never done that in the history of ever. All right. I haven't. That's something I never do. I would say I did it on purpose to see if you were listening, but I really didn't do it on purpose. All right. I just saw 2 eyeballs over there were looking at me very warm. You guys probably were too. Yours were closed.
Try on this, Larry.
All right. Now, technically this isn't done though, because what do I need to divide it by? dx dt, which I already did, so that the ingredients are already there. But I wouldn't divide it by dx dt. I would multiply it by the reciprocal, since it's a fraction. So I'm going to go like this. Are you okay with what I did? Because I'm just trying to make your lives easier. All right. Then I would even take this guy and write it with an exponent, because I know I'm going to have to plug 4 in there, and I really don't want to do it into this. Correct? So here's what I would do. I would multiply it in and get 6t to the 1/2 plus 1/2. That's nice. Plugging a 4 into there is 24. That's glorious. Minus a 2t to the -1/2 plus 1/2 is 0. Now it's really nice. So this is your second derivative right here. It's perfectly good for an FRQ, right? Multiple choice, you might not see it. It would look at like 6t minus 2. And then we were supposed to do it when t equals 4. So my second derivative is 24. Concave up or concave down at that time and place? Up. Okay. And then I don't want to do a ton of those because they're putsy. Are you guys okay with the process? Okay, the only thing I want to do now is switch to trig. All right, go to your calculators and try to graph this sucker just so you can go ahead and let's talk about how to set your window, because this is what I did skip. This is what I skipped in the pre-calc of it. All right, so when you're setting your window, obviously you're going to put this into your x of t, this into your y of t. What I would like you to do though is think about your x min. What is the most sine can be?
1.
1. Okay, so the most sine can be is 1. So the most this can be is you're going to kind of have to think it out, like what 2 minus 2 cosine t, the least it's going to be is 0. The most would be is negative 1. So I'd say your y is to go from 0. Otherwise, you're going to be, you can even kind of see up here, it doesn't get past 4 because this can't get past 4. Does that make sense? I mean, otherwise you just can fart around with your window, but if you think it out, it's a little less work. And I just want you to, this is how it's moving, like this, and then it does this, and then it kind of keeps continuing to roll on your calculator like that, right? I have it on mine as well. The first says to find the slope when t equals 1. Finding the slope is just dy dx. So let's go do that. It's a nice, pretty straightforward one. It'd be dy dt. What would the slope of that guy be? dy dt. Got it for me? What do you think, Linz? What's dy dt? Yes, because cosine's derivative is negative sine. 2 goes to 0, so that just is 2 sine t. Dx dt would be 1 minus 2 cosine t. Just easy derivatives. I'm supposed to do it at t equals 1. Okay, so I would do 2 sine 1 over 1 minus 2 cosine 1. This would be calculator active. By the way, do you see my bad notation there? Just because I'm getting a little sloppy. Do you see why you'd lose a linkage error here? Like, I put this equals this, which equals this. I really should do this. I'm getting a little sloppy, but technically I should be putting that on there. I don't know what that is. You guys go do it on your calculator. Make sure if you're in AP Physics, you're in radian mode. Go to 2 sine 1 divided by 1 minus cosine 1. It'll give me the slope of the tangent line when t equals 1. And I think you're going to have a very positive large number. I don't know what it is though. 2 sine 1 divided by, and put it in parentheses, 1 minus cosine 1. Is it very, very negative? It's hard to tell because it's this one right here. And it must be just tilted a little bit that way. I was thinking it was going to be, I was debating whether it was super up or, you see what I was debating? Yeah. So negative 20 point something. Let's go to 3 decimal places to be good kids. Negative 20 point what?
879.
879. That's the slope right here. So it's almost vertical, but not quite. Then it says where. This is where you have to be careful on a test. Circle that. If it says when, what answer are you looking for? T. When it says where, what are you looking for? Points. Yeah, so it says where is the curve horizontal? Well, you need the derivative to be 0. Now your derivative's always a fraction, correct? The numerator has to be 0. So all you really need is for dy dt to equal 0. Keep in mind, I want you to write this though, dx dt can't be. If they're both 0, what you see on graphs is like if we made a heart in parametric, both are 0 at the cusps. Okay? So just the top being 0 and the bottom not. So we're just going to go grab our dy dt, which we already did. It was just 2 sine t has to equal 0. And I just have to make sure that my answers don't make dx dt equal to 0. So that just means that sine of t equals 0, correct? Now I have to travel around the unit circle. L, where is sine equal to 0? At, where else? Where else? Because there's no domain on this. Where else? Where else? Dot, 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 n pi. Right? There's no domain. That thing's just going to keep cycling. Can't remember the name of it. It's not a hypocycloid. It's a, I don't remember what that graph is called. I'd have to Google it. It's got a name. Is this the answer? No. You have to go take those t's, and just like we always did, you have to plug them in to what? used to always say this last year. He said, you gotta plug it in. And I said, to what? The original function. We're not gonna obviously list an infinite number of points, but we're gonna start. When t is 0, x is 0. When t is 0, 0. So what we're saying is right here, there's actually a little horizontal tangent line. You can kind of see it curving there. All right. The next one would be when t is pi. Let's go do it. When t is pi, this guy's going to be pi minus 0. Right? So x is pi. How about this one? 4. Yeah, because it'd be negative 1, 2 plus 2, so it'd be 4. I'm going to take it out a couple more because you're going to see a pattern. The next one would be 2 pi. Back over here. And you might say, why are you putting in for the x? Because this is where that's always going to be 0. When I put in a 2 pi right here, what am I going to get? What am I going to get again?
4.
Yeah. There's a gnat. Or a piece of fuzz. Do you see it, Lainey? No. It's just floating right in front of my face. Anyway, the last question. Where is t with the curve vertical? What do you think you do? The bottom has to be 0 and the top is not. Let's just go find the first place where it happens because I feel like I've talked a lot. So we need dx dt to equal 0. And kind of keep in mind the top can't. And just so you were paying attention, what did I say happens when both of them are 0?
Hard.
You get a cusp. So like I don't know what the graph, this one looks all roly-poly, so I kind of know that that's not going to happen anyway, but we might have somewhere it kind of goes like this and like this and like this and like this, and these are the places where both are 0. All right, so where is dx dt equal to 0? It'd be where 1 minus 2 cosine t equals 0, right? So cosine t has to equal a half. 100% sure where does that happen? Let's start listing them. Where is cosine equal to a half? Give me one.
Pi over 3.
Pi over 3 is one of them. Okay? That's this guy right here. The next one isn't until this guy over here. What is it? 5 pi over 3. The next guy is 7 pi over. This is a pi over 3, one of them, right? So this would be at 7 pi over 3, and then I'd have to go 4. It'd go 11, and then 13, and then 17. You know what I mean? So 11, 2, 4, whatever. Dot, 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 dot. And then technically I have to plug it in to get the what? Points. And I'm getting tired of doing it. All right. Nothing's due tomorrow, but I do want you guys to try and see if you've got enough in you to answer 4 AP multiple choice questions, and then I'll tell you what you're going to work on for tomorrow. It's very short. We're going to do 1 through 4 on a worksheet. It's going to take about 10 minutes. But here's 4 past AP questions on parametric derivatives. And I know I went fast, but the ones I did are harder than these. Peyton's got E for the first one. Do we agree?
Yes.
Embarrassing if we didn't. Somebody's got E for the first one. I didn't know that. Sorry, Peyton. Luckily you were right.
I was just wondering if I had to answer.
Oh, because guess what I want you to do? On a different sheet. Yes. the second one, how are you gonna get your point? Plug the t in, yep. Get your derivative, dy dt over dx dt. And then it looks like the answers are in standard form, so you might have to move stuff around. So you guys get a slope of negative 1/5? Yes. Okay. And what was your point? Plug stuff in. Negative 3/1? Yep. And then yes. Negative 1 cubed plus 2 times negative 1. Negative 3. I agree with the negative 3/1. When you get it to here, I just want to remind you of some algebra. What don't you like about your form? It's a fraction. How can you get rid of it? I would multiply everything through by 5 or negative 5. I don't really care. I'm just going to go through by a 5 and get a 5y minus 5 equals a negative 1 times x plus 3, and then solve that. 4. Looks like you have to get it in a standard form, so it's going to be a plus 5y and x plus 5y. Then it doesn't even really matter. I'm seeing the last bullet. For vertical tangent, what's the only thing you're concerned about being 0? Yeah, x isn't moving and y is. That kind of makes sense, doesn't it? That dx dt would be 0 because when you're vertical. And then the last one's super easy. It will be. I'm going to explain it. Think should be dx dt. If you're finding horizontal. I bet you find your answer. Oh, you're being very careful. Good girl. Do we agree with the 1997 one being 0 2/3? Mm-hmm. And this one's really easy because it's just make sure you don't say 5/3. It's dy dt over dx dt for 3/5.